All right, so we've gone ahead and done integration with, well, working with definite integrals. And so we've looked at definite integrals and we've worked with indefinite integrals. What was the difference between an indefinite integral and a definite integral? Like if I just wrote one down, what was the difference between them? Like if I gave you something like this, I'm going to write a random thing. I don't know, x squared dx. Is that a definite or indefinite integral? Yeah, it's a definite integral. How'd you know it was definite and not indefinite?
Because it's one and two, so those are defined, they're not variables. So we have a set variable.
So it does have to do with the bounds, but it's not because it's just numbers. If I have upper and lower bounds, we say it is a definite integral. Compared to if I just wrote this, we call that an indefinite integral. It doesn't have bounds. Some other things that were different is that whenever I worked with this, my answer had a plus c at the end of it. Whereas where I was working with what up here, I did not have a plus c. All right, so we've worked with playing around with these integrals and antiderivatives. Now let's go ahead and work with what I like to hope. Let's add a little bit more, I'll word it as more interesting integrals on how we work with it. So you don't have to write this just yet, but what if I had something like this? I'm going to give you two quick things. Versus if I had sine of 3x dx. Let's think about this. For the one on the left, if I want to integrate sine of x dx, really we're asking the derivative of what function gives me sine. So do we know, remember, the derivative of what function gives me sine of x? Positive sine in particular. Negative cosine, yeah. So if I did this one, we would say this is negative cosine of x plus c. And we can double check derivative of cosine is negative sine, so negative sine, we plus a constant in our final answer. All right, that's great. But now I'm wondering, how does that 3x inside of the sine change? How would I even deal with that? Do I know of a function where if I take the derivative, it gives me sine of 3x? Well, it looks very similar, so maybe we want to look at this here. So what if I just wrote this, negative cosine of 3x? What's the derivative of cosine of 3x? Negative cosine of 3x. Well, derivative of cosine is negative sine. So we still get sine of 3x. But because of chain rule, let me write this down. If I took the derivative of this right now, I would get negative sine of 3x. And then because of chain rule, we'd multiply by 3. So this is not exactly right here, but we can do a very small adjustment to make this correct. What's standing in the way from this to my real correct answer? Yeah, this is already good. So far, if I clean this up, I get sine of 3x, for example. But I don't want 3 sine of 3x. I just want sine of 3x. So somehow I got to get rid of that 3, right? What's a quick way to get rid of a 3? Well, the 3 is not alone, it's a coefficient. So how do I turn a 3 into a 1? Can I add, subtract, multiply, divide? Yeah, I can say divide by 3, right? 3 divided by 3, I get 1. So what if I did my adjustment here? Let me erase this. What if I put a 1/3? Let's see if this will give me the correct derivative. So 1/3 stays along for the process. Derivative of cosine, we have negative sine. And because of chain rule, we multiply by the derivative of 3x. So 3. So negative, negative cancels out. 1/3 and 3 cancels out. I'm left with sine of 3x. So I know that this is actually the antiderivative of sine of 3x. So that wasn't too bad because really I had to adjust my constant up front. But what if I had more complicated stuff? How can I handle what if I had, like, for example, I don't know, x sine of 3x squared or something like that? Remember what I mentioned a while back whenever we talk about integrals? Well, the derivative, we know how to get the derivative of pretty much most functions that we work with. And we know that if I know the rule, then I can get the derivative. But unfortunately, in the opposite direction, the reverse isn't true. If I have a function, getting the antiderivative, that is integrating it, can be a lot more difficult compared to getting the derivative. So today we're going to learn the first technique beyond our quote unquote basic integration. So now this is the part where we can start writing stuff down. I'm going to call this the substitution method. O-N method. Substitution method. So I'm going to go ahead and start by writing out a theorem. And if you look at this theorem initially, it might look a little bit weird. Let's let big F be an antiderivative of little f. Of little f. Then the following equality holds true. The integral from a to b of f of u of x times u prime of x dx is equal to big F of u of x, from a to b. In other words, we'll focus on the exact notation here a little bit later, maybe not today. We're going to talk about how do I integrate these more complicated functions, like what we did with sine of 3x. In other words, what if I don't have my plain function template? What if it's not sine of x or cosine of x? What if it's not x squared? What if it's something that's more complicated? In other words, what if I have a function inside of a function? If we want to word it a certain type of way, this is not really the true name of it, but this is going to be, in a sense, the reverse of the chain rule. So this substitution method is going to be the reverse of our chain rule. Because for a function times its derivative, that's chain rule exactly. So we're going to see how do we undo the chain rule. And actually the best way for us to go about this is actually going ahead and doing a couple of examples. And I'm going to lead you through the first one or two, and we're going to start seeing how do I figure this out. I'll give y'all some time to copy this down as needed. Today we're going to focus on indefinite integrals, but then tomorrow and on the next day after that, we'll focus on definite integrals that use this method. So this is called the substitution method, or you can hear sometimes me say U-sub. This section will also emphasize why I was always so particular about putting that dx at the end of the integral. It's not just because of notation. Well, no, the notation is important, but it's going to come into play in our method today. And we're going to see how many examples we can get through. U is just another function. So remember how chain rule we had a function inside of a function? This is kind of the same idea, which is why I was saying earlier, it's kind of like going to be the reverse of our chain rule. So we are going to be throwing some letters around here and there in our problem solving, but as long as we're consistent, we should be able to follow through with it. All right, I think I still see a couple of people copying it down. I'll give you some more time. So what I want to emphasize here is that in my integral, what's going to end up happening is I'm going to look for a function u, typically on the inside, such that I also see the derivative of that function in my integral. So let's go ahead and do our first example and see how we handle this one. Evaluate. Evaluate is how you spell it. Let's say I have the integral of 3x squared sine of x cubed dx. So looking at this is definitely not our standard vanilla function like sine of x. In fact, we have a couple of things going on here. So as I said, I'm going to lead y'all through this first one. And I'm going to ask you how to see how this particular choice I make will actually help us. So do I see a smaller function on the inside, but also see its derivative in the function somewhere? So there's something here where I see it and I also see that the derivative is in the problem as well. Yeah. So what do you think I'm talking about? Yeah, so if I look at x cubed, let's go ahead and write that. I'm going to write u. Let's make that x cubed. So I have x cubed. And I'm going to use this new notation. Let's write du, in a sense, the derivative of u. What's the derivative of u here? Yeah, we have 3x squared. And I'm going to put a dx after it. So here I'm going to use, in a sense, the derivative of u is 1 du. Derivative of x cubed, here we get 3x squared dx. Yes, you can think of it that way. We took the derivative of x, so we put a dx there. And we're going to see why is that helpful for me here. So if I want to rewrite this integral, I replace x cubed with a u. So this is u now. So let me write that down. That's sine of u. And notice this as well. 3x squared dx. That's exactly what I have right here. So 3x squared dx, oops, that is exactly du. So I can actually move this a little bit over to the left. So I replaced x cubed with a u, and I saw that 3x squared and dx together, that makes du. So I just replaced them with the du. This is my important step, the big step I'm taking here. So do we see how I got instead of the original, the integral of sine of u du. So why is this helpful for me now? Well, we know how to integrate sine. What's the integral of sine? That is the derivative of what function gives me sine again? Yeah, we have negative cosine. And notice here, my integral had u. So here, I should also write u. So negative cosine of u plus a constant. I'm not done just yet, but this is me integrating. Again, the reason I went through this is that now, by doing this substitution, I turned this original integral into essentially a vanilla integral, as something plain that we have actually seen before. So there's one last thing I want to do. I started off with x's. I want to end with x's. I don't want to start with x and then end with u. So I want to somehow go back to x's after the long run. But fortunately, I know how to do that. I know that u is the same thing as x cubed. So really, I can just rewrite this and say that this is the same thing as negative cosine of x cubed plus c. That's definitely in terms of x. And we can always check our answer. If I did this correctly, that is, if I took the derivative of this, I should end up back with this expression. So derivative of negative cosine, we get positive sine of x cubed. Chain rule says multiply by the derivative of x cubed, we have 3x squared. So this should tell us that our answer is in fact correct. So what we just did here was a U-substitution. I identified U and its derivative. And I saw that the derivative was actually in the original problem already. So in a sense, I'm exploiting the fact that we have it in here. We're actually really fortunate here that my derivative of x cubed, 3x squared, was actually perfectly there. And we're going to find out very soon that I didn't necessarily need this 3 right here. If it was x squared in front, I could still fix this. And we're going to see how in the next couple ones. But any questions about this example 1? As I said, typically the most difficult thing for our law students is identifying the U. Because after the U, we actually go through a fair bit of algebra as well. Let's go ahead and try this example 2. Same instructions. I'm not going to write evaluate again. What if I have the integral? Let's do x times x squared plus 9 all to the 5th power dx. So again, I'm going to lead y'all through and figure out what u is here. I want to find and define u to be one whole expression such that I can see that its derivative is in the original somehow. So let's consider this here. What if I let my u be x squared plus 9, for example? Let's say I let that happen. Then if I want to take the derivative and get du, what's the derivative of x squared plus 9? Yeah, we get 2x dx. So the first thing where I'm probably noticing here is that I don't have 2x in my original. This is where I'm going to play it out slightly differently. And actually, this is the method that I'm going to be pretty consistent with. What if I did this? Looking at it, let's say I divide the left and right by 2x, for example. That means here on the left, I get du over 2x is dx. I'm going to focus on this and what I wrote here. And I'm going to show you why this is actually going to help us a lot. So this first x, I didn't do anything with it directly for now. I'm just going to copy that down. X squared plus 9. I said, let's turn that into u. So instead of x squared plus 9, I write u, in fact, to the 5th power. So that's me replacing this right here. And we have a dx here. Well, I know what dx is. Dx is exactly du over 2x. Let's see where that takes me. Du over 2x. So let's break this down here. Do I notice any cancellation here? If I look at this, well, I have an x on the top and then an x on the bottom. So those can cancel out. And I'm going to take a slight pause here and note this is important because I do not want to integrate my integral when there are two different letters in it. I want to make sure that I have only one variable that I'm working with, at least at this point of calculus. So I'm going to do this one step at a time. I have u to the 5th du over 2. Or you can put the whole thing over 2, still the same thing. So you can see here, by solving for dx, I can just very directly plug in for dx and u in the original. Now I claim that y'all are able to integrate this, u to the 5th over 2. So how do I integrate u to the 5th over 2? What does that integral equal to in terms of u? No, not exactly. Remember, we have one special rule for integration that we've definitely learned about. This is just my variable to a power. So let's use the power rule for integration. What is the power rule of integration telling me? What do I do to the power? Yeah, we add 1 to the power. So 5 plus 1, we get 6. And then do I multiply by that new power or divide by the new power? Yeah, we divide by the new power. If I divide by 6 on the bottom, that gives me 2 times 6 on the bottom. 2 was already there. Dividing by 6 puts the 6 down there. Plus c. And now we're going to continue to clean this up. U to the 6, for now, I'm going to leave that alone for this step. 2 times 12, I already said it already. 2 times 6, we get 12, plus c. Am I done with this as my final answer? No, why not? Yeah, I started with x. I want to end with x. Fortunately, I know what u is. U is exactly x squared plus 9. So instead of u, I can put x squared plus 9 to the 6th power all over 12 plus c. And I can tell you here that if I took the derivative of that expression, I will definitely get back to this original. This is also why we really emphasize the whole semester on taking derivatives. Because if you can take the derivative, then you can always check your answer in Cal 2 whenever you do integrals. All right, so we have example 2. Any questions, comments, or concerns about that one? All right, so let's see what I can do here. I'm going to give y'all a problem, and I'm going to see if y'all can actually solve it. Oh, yeah. So this is going to be, let's do this as, my bad. All right, example 3. Evaluate the following integral. Let's say I have the integral, let's do, let me see, how do I want to word this? Let's do start off nice, cosine of x, e to the sine of x dx. So take some time and see if you can figure out first what is u, then what is du. Using that, you should be able to clean up this integral and make it into something that's a little bit more quote unquote simple. And a big trick of it is usually you want your u to be something where if you take the derivative, you also see the derivative by itself in the function, typically being multiplied to be exact. So I'll give you all a couple of minutes to see how to take this on. So identify what should be u, what should be du. And if we did it correctly, it should turn the function into something that is a little bit easier for us to look at. Again, choose u such that you can also see that the derivative of u is in there somehow. And really, we only have a limited number of choices on what we can choose for u here. So what do y'all recommend I use as u for this problem? Yeah, I would agree with that. Because if I let u be sine of x, we know the derivative of sine is exactly cosine of x dx. Because here we're taking the derivative. Derivative of sine is cosine. Yeah. And that's one of the tough things, especially whenever we're doing trig functions, is going to be a little bit of work to try to reroute our brain, say, are we going up? Are we going down? Things can get a little bit confusing, especially with the positive and the negative. All right, and just for practice, let me try to solve it in the same way I did as example 2. Let's say I just want to solve for dx here. If I want dx alone, I can divide by cosine of x on the left and the right. I know it's not really necessary for this problem, but it's good practice to do this here. That would give me that du over cosine of x is equal to dx. So I'm going to plug in this, and I'm going to plug in this here. Again, I know that you probably could do it from the beginning, but this is going to be good practice, especially whenever it doesn't match exactly. So looking at this original, I have the integral of cosine of x times e to the, I replace sine of x with u, so of e to the u power. And instead of dx, I have du over cosine of x. And if I am fortunate, then all of my x terms should cancel each other out somehow. So let's see. I have the integral. Cosine cancels with this cosine of x, leaving me with the integral of e to the u du. Now I want to figure out what's the integral of e to the u. That is, what function, if I take the derivative, I get e to the u. Yeah, so looking at this, I want a function where if I take the derivative of it, I get e to the u. Well, that's still e to the u. Because I know if I take the derivative of e to the u, I get e to the u. And it actually, as it turns out, it's the same backwards as well. Integral of e to the u is e to the u, because we have that relationship. Plus c. And then, zoom out a little bit. I don't want u in my original answer, my final answer. So I should put back my u, whatever it was, giving me e to the, instead of u, I have sine of x plus c. And again, we could verify my answer if I take the derivative of that. The derivative of e to the sine of x, I get e to the sine of x times the derivative of sine, which was cosine, which is exactly what I have in this original problem. So we can verify our answer that that is in fact true. All right, so any questions about this one? I have one more example for y'all to see if y'all can decipher this one. And initially it's gonna look, it might look deceptively something that we can do quickly. Well, I say deceptively because we could actually do it pretty quickly. Let's do example 4. I'm gonna call this one example 4. Let's say I have the integral of, let's do the natural log of theta over theta d theta. Remember, I'm not necessarily restricted to x. I could use whatever letter I want. So now I'm going to figure out, wow, what's going on here? So I'm going to see if there's a u that I can choose here, such that the derivative also belongs in the original. So do I have any ideas about what could I possibly use for u, and then hence du? Well, we're kind of limited on choices here. What do you think I could use here for u? Let's see what happens if I try natural log then. Let's see if I let natural log u be natural log of theta. What's the derivative of natural log again of theta? Yeah, 1 over theta d theta. And again, just for the sake of continuity, let's go ahead and solve for d theta here. just get in that habit. To solve for d theta, I can multiply the left and right by theta, giving me, for example, theta du is equal to d theta. So I'm going to use this and my original. And let's see if that helps me or not. Hopefully it does. I have the integral. Natural log of theta. We said let's make that into a u. I still have theta on the bottom. And then d theta. Well, d theta is theta du. Well, that's great because now we have theta on top, theta on the bottom. We have that they will cancel out to give me 1, leaving me with u du. What's the integral of u to the 1 power? The integral of a plane u. So we talked about this one a little bit earlier. Kind of similar whenever we had u to the 5th power. We had that rule. We can do the same thing here because it's just, yeah, y'all are correct here. I add 1 to the power, divide by the new power. So we get u squared over 2 plus c. Can't forget the plus c here. And now, again, I don't want my answer in terms of u. I want it in the original letter, or in this case, theta. So instead of u, I have natural log of theta. So natural log of theta squared over 2 plus c. And then I have my answer. So the integral of natural log of theta over theta is actually natural log of theta squared over 2 plus c. And if you wanted to, you could check your answer by taking the derivative. If I take the derivative of that expression on the right, I should get back to that original in the beginning. And this is going to be something that's consistent through pretty much all of our integrals that we work with. So what I want to note about this, some last notes about here, is that we learned a new technique of integration, and then this expands the amount of functions that we can now integrate. But there is something unfortunate about this method. It does not work for every type of integral we encounter. In fact, this covers only a very tiny portion of possible functions. What's going to happen in Cal 2 is that you're going to expand the versions, the types of functions that you can integrate. But even after you complete Cal 2, most of the functions you still cannot integrate. You'll find out that there is a huge amount of functions that are not integrable, that you can't really find the antiderivative. And then you start getting into these other things where you maybe can get an estimate of it. And then we start getting into more other things beyond the scope of at least our Cal 1 class. So right now, we're still working basically a very limited integration method. All right, so besides that, that is going to be all for today. Tomorrow, we're going to work on what if I add bounds onto these? How does that change things? And it is going to require a fair bit of algebra. I recommend bringing a calculator tomorrow to help us get through these. All right, besides that, that is all for today. I'll see you all tomorrow.